Hi guys, chapter 23, section D. We're now dealing with binomial distribution. And this is going to be using binomial expansion. So thinking back to chapter 7, binomial expansion, but also chapter 22, probability. This is going to be sampling with replacement. So that means if I'm doing a trial, removing something and putting that back in and then doing that exact same trial again. That way the probabilities for every trial remain the same. Okay, so sampling with replacement. There's two things that determine whether an experiment is a binomial experiment or not. The first thing is there has to be only two things happening. Either we have success or failure. So success or failure. So either we're finding this thing we're looking for or we're not getting the thing we're looking for. Has to be able to be looked at that way. Probability of success and the probability of not getting success. Now, the second thing is a number of independent trials. So each trial is independent from the other, meaning that one does not affect the other. So that's going back to the with replacement idea. Okay, so binomial distribution, we think about binomial expansion. And here we have a binomial expansion situation. P plus Q in brackets, all to the power of n. Well, we know how to do this binomial expansion. Every single term in that expansion is going to look like this. N choose R, P to the power of R, Q to the power of n subtract R. And then we're going to do that again for the next term. For the first term, R will be equal to 0. For the second term, R will be equal to 1. For the third term, R will be equal to 2, and so on all the way to R being equal to the last term, n. Okay, now, for binomial distribution, where's my blue? Here it is. For binomial distribution, P represents the probability of success. Super important. Probability of success. Q represents probability of failure. So those two things will equal 1. Okay, so if we don't know the probability of failure, we can find it because Q will always be equal to 1 minus P. Okay, and N represents the number of trials. Okay, so our example is going to be this guy. It's a spinner in a game. The spinner has 4 sections, so we would spin it. Three of those sections are blue and 1 is white. So the probability of getting a blue would be 3 out of 4, and the probability of getting a white would be 1 out of 4. Okay, so let's move on to this example. Move this forward. Okay, I am defining X as representing the number of blue spins in this situation. So same blue spinner I had on the last page. Success is a blue spin, failure is not a blue spin. So we know that probability of success is equal to 3 out of 4, and the probability of failure is equal to 1 out of 4. Okay, sorry about that smudge in my paper right there. All right, so we can think of this binomial expansion, this binomial distribution and binomial expansion situation. P plus Q to the power of n, which in this case would be 3 out of 4 plus 1 out of 4. And we're going to spin it 3 times, okay? Spin the spinner 3 times. Okay, so that means our power, the n, is 3. Okay, now you could look at this and say 3/4 plus 1/4 is 1, and then 1 cubed is 1, but we're not going to think of it that way because the 3 over 4 is the probability of success. The 1 out of 4 is the probability of failure. Thank you for the treat. Okay, so when we do this expansion, we will have 3, n choose R. Remember it looks like this. N choose R, P to the power of R, Q to the power of 1, n minus R. Okay, so we need to remember how to do binomial expansion. Okay, so the 3 here means we're using the third row in Pascal's triangle. So remember Pascal's triangle. Okay, there's Pascal's triangle down to the third row. So our binomial coefficients will be 1, 3, 3, 1. And then we take 3/4 for all of these. First one being the highest power, so power of 3, and then power of 2, power of 1, power of 0, or you could just not write it in there because 3/4 power of 0 is 1, and then 1/4 on all of them. And here, start with a power of 0, so you could choose just not to write that one because 1/4 power of 0 is 1. Power of 1 here, power of 2 here, power of 3 here, and plus signs in between all of these for the expansion. Okay, we can go ahead and multiply those all out. 1, this is going to be 1, so 3 cubed is 27, 4 cubed is 64. Here we have 3 times 3/4 squared times 1/4, so that will also be 27/64. Okay, here 3 times 3/4 times 1/4 squared, so that will be 9/64. And here 1 times 1, because 3/4 power of 0 is 1, times 1/4 cubed, so that's 1/64. Now, if this is a binomial distribution, then all of these probabilities should add up to 1, so let's just check that. 27/64, 27, that would be 54. And 10 more, 64/64. So it works. They add up to 1. Okay. What this actually means is the probability. So it's 27/64 means that's the probability that we will have 3 successes. So on these 3 spins, all 3 will be successful. This is successes, the thing that we're looking for. So a blue spin. This term here, 27/64, means we will have 2 successes and 1 failure. And there's 3 different ways that can happen. And we'll talk about that with the tree diagram in a minute. This term, the third term, means 1 success, 2 failures. So out of those 3 spins, we would end up with 1 spin that got blue, 2 spins that got white. Chances of that happening are 9/64. And the last term, there's 1 way for this to happen. All 3 will be white. And the probability of that is, of course, lower, 1/64. Okay, so if we think about chapter 22, probability, and we have a tree diagram, this first branches in the tree represents the first spin, second spin, third spin. The probabilities for each of these will remain the same, independent trials, they're independent. So for every one of these, the blue will be 3/4. So I'll put that in everywhere. Hopefully you can see this. And for every single trial, the probability of getting a white is 1/4. Okay, so what happens in this situation? We end up with, following those branches, blue, blue, blue. Okay, so all 3 are blue, and we multiply across those branches, 3/4 times 3/4 times 3/4. That's 27/64 for a probability. Notice that this matches the first term here, which also had the same meaning, 3 successes. And there was only 1 way of that happening. Okay. I'm going to do the next one in a different color here. It's red. Here we have, in this pathway, blue, blue, white. Blue, blue, white. The probability of that happening is 3/4 times 3/4 times 1/4. So that's 9/64. Okay, in this next path, blue, white, blue. Blue, white, blue. Also 2 blues. So this is also 9/64. And I'm going to skip this one for now because that's 2 whites. I'm going to come down here to the 2 blues. White, blue, blue. If I multiply across there, I also get 9/64. So you can see these three added together are 27 out of 64. They all result in 2 blues. So if we look back up to this 27 out of 64 and look at the binomial expansion part, that term up there, there were 3 ways for this to happen. Well, there's the 3 ways. 1, 2, 3. 3 ways of getting 2 successes and 1 failure. And you can see those are the ways. Either the first one will be a failure, or the middle one will be a failure, or the last one will be a failure. Okay, so another color here. Here we have blue, white, white. So blue, white, white. If I multiply across there, we get 3 out of 64. Here we have white, blue, white, white, blue, white. And again, multiply across, 3 out of 64. And here, white, white, blue, white, white, blue. Multiplying across, we again get 3 out of 64. Add up these green ones, we get 9 out of 64. And up here, 9 out of 64 was this term in the expansion. 1 success, 2 failures. So 1 blue, 2 whites. There's 3 different ways for that to happen. That's what the binomial coefficient represents. 3 different ways. So those are added together. And the last way is white, white, white. That's 1 out of 64. There's only 1 way for that to happen. And there's the 1 out of 64. There's the last term that represents that. 1 way for it to happen, no successes, 3 failures. So that's how those all relate to each other. Binomial distribution with probabilities. There we have it.